Find the derivative of the function at the given value. All right, so first let's find the derivative, and then after I find the derivative, I have to plug in 3, and that's what it's asking me to do. So in order for me to find the derivative, I want to use quotient rules. So let's call u u, let's call u v. I need to find out what u prime is. So u prime is going to be nothing. That's going to make life a little bit easier when I get there. V prime is going to be 2x rather plus nothing. And then I have v squared, which is going to equal x squared plus 5 squared. And I'm not going to FOIL that out unless I have to. Okay. Quotient rule is u prime v minus v prime u over v squared. So I'm going to put it all together. Y prime is u prime, so nothing, v, which is who cares, minus v prime, which is 2x, u, which is 20, over v squared, which is x squared plus 5, all of that squared. Now, my job is to find out what the derivative is when x is 3. So I need to find y prime of 3, which you're useless, is going to require me to plug in 3 for every x. So I have nothing minus 2 times 3 times 20. Okay, that's that chunk right there. All over 3 squared plus 5, all of that squared. So I have negative 6 times 20, so negative 120. Over 9 plus 5, which is 14, 196. Divide that by 4, you get negative 30 over 196 is 49? Yeah, that's it. It doesn't simplify any further than that. So yeah, that's my answer. What this means is find the derivative means slope of the tangent line. So what this means is if I were to graph that guy right now and say, you know what, I wonder what the slope is at 3. There it is. Couldn't look at it and guess it, but that's what it is. Negative 30 over 49 is y prime 3. Fun, 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 fun. Find the derivative of the function at the given value. So I have to take the derivative of negative tan 2x, and then when I'm done that, plug in negative pi. All right. The derivative of tan is secant squared. All right. But this isn't tan. This is tan 2x. So this requires a chain rule. So the chain rule is you take the derivative of the outside stuff. So the derivative of negative tan of stuff is negative secant squared of stuff. Keep that stuff, but then multiply everything by the derivative of the inside stuff. So this ends up being negative 2 secant squared 2x. That's what y prime is. But I don't want y prime. I want y prime of negative pi. So I have to calculate negative 2 times secant squared of 2 times negative pi, or negative 2 pi. Fun fact, secant squared of negative 2 pi is 1. How did I do that so fast? I paused the video and typed it in. So when you multiply negative 2 to it, you get negative 2, which means, find the derivative. Derivative means slope. If you learn anything from calculus, it's that derivative means slope. So if I were to go to negative pi, look at this graph, and wonder, I wonder what my slope is, it's negative 2. So that's how it's done. Take the derivative of y equals the inverse cosine of negative 5x to the third. Well, that's inside stuff, so I'm going to put parentheses there. First things first, the derivative of an inverse cosine, I'm going to write it up here, is negative 1 over the square root of 1 minus x squared. Now, that's if it's just the inverse cosine of x. This is the inverse cosine of stuff, which tells me I'm going to have to deal with a little bit of chain rule because the stuff is not just x, it's a little bit more. So what I'm going to do is I'm going to take the derivative using the chain rule, which is, chain rule in general is you take the derivative of the outside stuff first. So we're going to write out negative 1 over the square root of 1 minus, however, keep the inside stuff. So I'm going to keep, instead of x, I'm going to write out negative 5x cubed. So this is me keeping the inside stuff. Don't forget the squared. Let's make that a little bit bigger. But then you multiply everything by the derivative of the inside stuff. So the derivative of the inside stuff is going to be 3 times negative 15. Negative 5, which is negative 15. I'm jumping the gun in my head. Turn that x to the third into x squared. And then maybe my last step would be for me to take this guy, scooch it up here. I have a double negative going on, so maybe those negatives cancel out. So let's pretend that that negative wasn't there, make it a positive. 15x squared. On the bottom, I have the square root of 1 minus, and negative 5 times itself is 25. X to the third times itself is x to the sixth. Can't do much more than that, so that's going to be my answer. Pretty gross. Find the derivative of the inverse of 5x equals negative 4x cubed minus 4. All right, so what I need to do is find the inverse of that. What you do whenever you find the inverse, and right now what I'm going to do because it makes my life easier is I'm going to pretend that f of x is y. So I'm going to pretend that f of x is y. Whenever I'm finding the inverse, the first thing I need to do is I need to swap the x and the y and then solve for my new y. So this is me doing exactly that. In order to get y all by itself, you have to add 4, crosses out. Now I have x minus 4 equals negative 4y to the third. I'm going to divide everything by negative 4, so divide everything by negative 4, divide everything by negative 4, So I have negative 1/4 x plus 1 equals y to the third. Now I have to cube root both sides. Cube root both sides, and that gives me y equals, now watch how I know what's going to happen. If I'm going to have to take the derivative, that cube root doesn't do me any good. I'm going to put it as to the 1/3 power. I have negative 1/4 x plus 1 living in my parentheses, so that becomes that. Now I'm going to write that out as the inverse. Now that's not my answer. I just have to find the derivative of that. Now finding the derivative of this guy requires chain rule. So you have the inside stuff, which is there. You have the outside stuff, which is there. So the derivative of the inverse is going to have me taking the derivative of the outside. So bring that 1/3 out front. 1/3 minus 1 is going to be negative 2/3. Keep the inside, so negative 1/4 x plus 1, and then multiply everything by the derivative of the inside stuff. The derivative of negative 1/4 x is just negative 1/4. That's supposed to be the end of the parentheses, but something happened there. Plus 1, nothing. So let's clean this up a little bit. All right, I now have this big fraction where so far 1 is on top, 3 is going to be multiplied to -4, so let's make this whole thing negative. So 3 times 4 is 12. And then I have on the bottom, because I can move this down, -1/4 x plus 1 to the 2/3, leaving me with just 1 on top. And that's good enough an answer for me. I think that's acceptable. It looks kind of gross. I mean, if I really wanted to turn this into a cube root of that guy squared, I could. But you know what? I've had enough. I've had enough of that problem. And that problem's good enough for me. Find the slope of the tangent line at the given value. All right, so the slope of the tangent line means if I were to go at -2, which is here, right, put a dot there, what is the slope of that line right there? Well, it looks like it's positive. Maybe it's 1. Looks like it's 1-ish, but I don't know. And that's what I need to find out. The way you find the slope of a tangent line is you take the derivative and substitute that value for x. So y prime of this polynomial right here is 2x, because bring down the 2, that goes to 1, plus, just get rid of the x, and the 7 disappears. Now what I do is I plug in -2 for every x value. So 2 times -2 plus 6 is the same as -4 plus 6, which is 2. So the slope of the tangent line, I initially guessed it was going to be 1-ish, but maybe my picture should have been better. Maybe it should have been steeper, in which case that picture would match up with this guy right here. So the slope of the tangent line at -2 is +2. That's all I have to do for that guy. Take the derivative, plug in your x. Find the slope of the tangent line at the given value. All right, so in order to find the slope of the tangent line, derivative means slope. All right, so the slope of the tangent line requires me to take the derivative of this guy and then plug in -3 for x. Now, the derivative of regular ln of x is 1 over x, but this isn't regular ln of x. So this is going to require chain rule. So chain rule is you take the derivative of the outside stuff. So my outside stuff is -ln. So it's going to be -1 over stuff. You keep the inside stuff. So you take the derivative of the outside stuff, keep the inside stuff, but multiply everything by the derivative of the inside stuff. So I'm going to multiply everything by -1 because the derivative of -x is -1 and the derivative of 2 goes away. So basically the only thing that changes is -1 times this whole negative thing becomes one whole positive thing. So I have 1 over -x plus 2. Now to find the slope of the tangent line at x equals -3 requires me to find y prime of -3. So y prime of -3 is 1 over -3 plus 2, which is 1 over 5. That's my answer. Slope of the tangent line means take the derivative. Find the equation for the tangent line at a given point. All right, well, the slope of a tangent line is found by taking the derivative of a curve or whatever we're dealing with and plugging in the x value. So let me start out with that. Let me take the derivative, y prime. That's going to give me drop down the 3x squared minus, drop down the 2 times 2 is 4, regular x plus 2 goes away. Now I take my x value and I find out that y prime of 2 of that guy is going to be 3 times 2 squared minus 4 times 2. 3 times 2 squared is 3 times 4, 12, minus 4 times 2, which is 8, gives me 4. Okay? So my slope of the tangent line is 4. So m, and I'm going to put m tan for slope of the tangent line is 4. What I'm going to do is I'm going to use point slope form to write out the equation of a line with a slope of 4. Why am I using point slope form and not like, slope intercept? Well, I have a point, and that point is 2, 2. So I'm going to write out y minus y sub 1 equals m times the quantity x minus x sub 1. This is the point that I'm going to use, x sub 1, y sub 1. My slope is 4, so I have y minus y sub 1, which is 2, equals 4 times the quantity x minus x sub 1, which is 2. Now, what this looks like graphically, all right, is graphing something like this. Graphing a cubic is going to give me something that looks like this. At some point 2, 2, I have a tangent line where a slope is 4. So again, the way we find this tangent line's equation is we start out by taking the derivative, plugging in 2 for x, and that gives me a slope of the tangent line. Once I have a slope of a tangent line, I have also a point of a tangent line. Use that point, and I can use point slope. And if you want to do slope intercept, then distribute, add 2, you'll get 4x plus minus 6, minus 6. So it all works out in the end. Fun, fun, fun. Find where the tangent lines are horizontal. Well, lines are horizontal when the slope is 0. You can get the slope of a tangent line by taking y prime, the derivative. So in this case, I want when y prime is 0. So let's find out what y prime is. Y prime is going to be drop that 3 down, drop the 3 to x squared, minus 2 times 2, which I think is 4, and drop that squared down to a single x, and the 2 just goes away. Now what I need to do is I need to set that y prime equal to 0, so I'm going to bring that over here, and I'm going to factor that guy out, which only has me pulling out the x and nothing else. So I have 3x minus 4. If 0 equals something times something, you're going to use the zero product property, and you take each factor, set it equal to 0. So x is equal to 0, and 3x minus 4 is equal to 0. Add 4, and you get that. Divide by 3, and you get that. So this is the x value. These are the x values, rather, where my tangent line is horizontal. Now, I don't know exactly what these values are, but this is a cubic. Cubics look like this. Okay? Cubics look like that. So at the very tippy top is where you're going to get a horizontal tangent line. And at the very bottomy bottom is where you're going to get a horizontal tangent line. I know this happens at x equals 0. I know this happens at x equals 4/3. What I don't know is the y value. But I can find the y value by taking 0 and 4/3 and plugging it into the original equation. Not the derivative, the original equation, because that gives me the exact locations as to where these tangent lines are horizontal. So let's do the easy one first. Let's find out what y of 0 is, which means I'm going to take 0, plug it into the original equation. So 0 cubed minus 2 times 0 plus 2 is going to be 2. So that, like I said, that was the easy one. 2 minus 2 plus 2. When I plug 0 into the original equation, I get 2, bada bing. Now, not the fun one. When I plug 4/3 into the original equation, I'm going to get 4/3 cubed minus 2 times 4/3 squared plus 2. 4 times 4 times 4 is 64. 3 times 3 times 3 is 27. 4 times 4 is 16. Times negative 2 is negative 32. 3 times 3 is 9. Plus 2. Let's make all of these have denominators of 27 so that I can combine fractions without having to use a calculator. So nothing changes there. If I multiply the numerator and the denominator of this guy by 3, that gives me 96 over 27. And if I multiply this guy by 27 over 27, I get plus 54 over 27, and now I can combine all of these fractions. So let's do the positives first because, you know, I like being positive. 64 plus 54 is 118. 118 minus 92 is 22 over 27. Just trying to do this all in my head, making sure I'm not making a mistake. And I think I'm okay. I think that's pretty good. Again, 64 plus 54 is 118. 118 minus 96. I'll take it. So by plugging in 4/3, I now have my 2 points. There they are. There they are. Let me rewrite them out in a color I haven't used yet. Where are these tangent lines horizontal? 0, 2. And 4/3, 22 over 27. There you have it. Now you know exactly. Now you know exactly what to do. Find the critical points of y equals stuff. All right, the way you find critical points is you take the derivative and then set that equal to 0. So let's take the derivative, y prime. Y prime is going to equal 3, drop it down, x, turn that into a 2, minus, drop the 2 down, make it a 22, x to the regular x, plus 39, and that's it. Now I have to set it equal to 0. So 0 equals, can't factor it out. Can't factor it out. But once I get to this point right here, I could use a good old friend called the quadratic formula. Maybe it does factor out. I mean, it doesn't factor out regularly. You probably can factor it out, like maybe using like 13s and 3s, but I don't know. I'm nervous and I'm not going to risk it. So I'm going to use the good old quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So x equals negative. So here's my a. Negative 22 is my b, and 39 is my c. So x equals negative 22 makes that positive 22. See what I did there? Plus or minus the square root of negative 22 squared minus 4 times a, which is 3, times c, which is 39, all over 2 times a, which is going to be 6. Ugh. All right, well, that'll become regular 20. Let's just use Siri. 22 squared minus 4 times 3 times 39. Oh, no way. It's 16. By the way, I said 22 because I knew that would become positive anyway. Oh, how nice is that? All over 6. So when you split this up into 2, x is going to equal 22 plus or minus 4. So we'll do plus 4 over 6. And x equals 22 minus 4 over 6. 22 plus 4 is 26. 26 over 6 simplifies to 13 over 3. 22 minus 4 is 18. 18 over 6 is 3. So these are my two guys. My critical points are going to be 13 over 3 and 3. Now for many problems, critical points might require you to find the y value, but for these, we're only going to find the x value. If you want to find the y value, you would just plug 13 over 3 into the original equation, plug 3 into the original equation. But this leads to a concept known as increase and decrease, looking for intervals of increase and decrease. And usually for problems like that, we don't really necessarily care about the y value. All right, so I'm going to leave it like that. Find where the function is increasing or decreasing. All right, so this is what I'm going to do. I'm going to find where the derivative is positive, because when the derivative is positive, that's increasing. When the derivative is negative, that's decreasing. What I need to do first is I need to find my critical points. Why? Because the critical points tells me where my derivative is 0. Once I get zeros, I can kind of break it up into intervals and figure out which ones are positive, which ones are negative, take it from there. So I have to take the derivative of this guy. So negative, bring that 4 down, turn x to the 4th into x to the 3rd. Multiply that 2 to 3, x squared becomes x to the 1st, and the derivative of negative 3 is nothing. I don't know why it took me so long to figure that out. Now, in order to find the critical points, I need to set my derivative equal to 0. While I'm at it, I'm going to factor negative 2x out, okay? Because 2 is divisible by these guys, the negative because I don't like my leading coefficient being negative, and there's an x in common with both. So when I divide out a negative 2 from negative 4, I get 2. And when I take an x away from x cubed, I get x squared. When I divide a negative 2 from regular 6, I get negative 3, and that's it. Now, the zero product property says that if I have 0 equaling two numbers multiplied together, or two factors rather multiplied together, I take each factor, set it equal to 0. So I have negative 2x equal to 0, and I have 2x squared minus 3 equal to 0. Divide both sides by negative 2, and one of my critical points is 0. Easy enough. Let's add 3 to both sides. Divide by 2, and x squared equals 3 over 2. Now be very, very, very careful. I have to solve for x, and the way I do that is by taking the square root. Do not forget your positive or negative. It happens all the time. So 2 other critical points, not 1, but 2 other critical points are going to be positive or negative 3 over 2. So 0, negative 3 over 2, and positive 3 over 2 are where my original function is going to have a slope of 0. So neither increasing nor decreasing. Now what I'm going to make next is something called a sine table, or a sine graph, or a sine chart. Now S-I-G-N, not S-I-N-E. Don't get excited. All right. I'm going to put my x values for critical points right here. The negative 3 over 2, 0, and square root of 3 over 2. Not negative, but negative square root of 3 over 2. I'm putting those there in order. What I'm going to do is I'm going to choose values in between these numbers, and bigger than and smaller than, and plug them into my derivative to see if those values give me an interval that's positive or negative. If it's positive, that tells me that everything between here and here, or everything between here and here, or everything there is positive or increasing. And if it's negative, decreasing. So I need to pick numbers that are not exactly these numbers. Now, if you're wondering, well, why can't you just pick these numbers? Well, if I take these numbers and plug them into the derivative, I get 0, which kind of defeats the purpose. The 0 tells me that that's where a change probably occurs in increasing to decreasing. So square root of 3 over 2 is like taking the square root of 1.5. So that's going to be bigger than 1, but not that big. So I can use 1 and negative 1 as potential numbers to plug in. I'll use 10 and negative 10 because why not exaggerate things? And I plug these into my derivatives. All right, so let's start out with negative 10. So y prime of negative 10 is going to be this guy right here, negative 4 times negative 10 cubed plus 6 times negative 10. Now, I'm not going to overthink this. I'm not even going to do any math. Negative 10 cubed is negative 1,000. You multiply that to negative 4 and you get 4,000. 4,000 minus 60 is going to be a huge number. But the most important thing is that it's going to be positive, which tells me that when I plug in negative 10, it's increasing. So this is why I call it a sine table or a sine chart, because by plugging in negative 10, I know everything from negative infinity to negative square root of 3 over 2 is going to be an increasing part of this function. Now, if you're like, well, that's easy, I'll just get negative, positive, negative. I don't know. Probably, but I don't know. So let's find out what y prime of negative 1 is. Okay, that's going to be negative 4 times negative 1 cubed plus 6 times negative 1. Negative 1 times itself 3 times is going to be negative 1. Negative 1 times negative 4 is positive 4. Positive 4 minus 6 is negative 2, which tells me that between negative square root of 3 over 2 and 0 is decreasing. Almost there. Y prime of regular 1 is going to be negative 4 times 1 to the third plus 6 times 1. 1 to the third is 1. Negative 4 times it is negative 4. Negative 4 plus 6 is positive. So that tells me that between 0 and root 3 over 2 is going to be an increasing function. Last but not least, let's plug in 10. 10 tells me what's happening after the square root of 3 over 2. So negative 4 times 1,000, or, well, 10 cubed, which becomes 1,000, plus 6 times 10 is going to be 1,000 times negative 4, which is negative 4,000. Negative 4,000 plus 60 is still going to be negative, so it stays negative. Boom. All right, now let's get rid of, I hate it, but we need to get rid of this to give ourselves some space. Okay? This is now telling me that everything is increasing. Everything is increasing on the intervals negative infinity to negative root 3 over 2. Also, it's increasing on the intervals 0 to root 3 over 2. And it's decreasing between negative root 3 over 2 to 0 and root 3 over 2 to infinity. So there you have it. Very, 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 very busy problem. Lots to do. But without graphing, I was able to figure out where stuff is increasing and decreasing. Find all points of discontinuity. Discontinuity means if I were to graph this, where will my graph break? Maybe it becomes a hole, all right? Maybe it becomes an asymptote. Where does that stuff happen? Well, easiest answer is this stuff happens when my function is undefined. Where is a function undefined? When the part in the denominator is equal to 0. So let's find out when 4x plus 4 is equal to 0. Okay, minus 4, 4x equals negative 4, divide by 4, x equals negative 1. So my one and only point of discontinuity, also known as POD, not to be confused with a really good nu metal band from the early 2000s, late 1990s. I like them. I've seen them live a few times. My one and only point of discontinuity is when x is negative 1. That's it. Also, big shout out to POD, a very good band. Find inflection points and where the graph is concave up and concave down. All right, before I do anything, let me remind you or let me teach you what's what. Inflection points are when what your x values are when your second derivative equals 0. Concave up on a graph is when you have parts of your graph curling up like that. That happens when your derivative is positive. Concave down, very similar, looks like this. That happens when your derivative is negative. So what I'm going to do is I'm going to take the second derivative, find my x values when my second derivative is equal to 0, and make a sign chart. So those of you who are obsessed with my YouTube, if you've seen my video on inflection points and increasing and decreasing functions, this is extremely similar, but we take it an extra step by taking the second derivative instead of the first derivative. All right, so first derivative, first things first, is going to have me bring down that 4, make it x cubed. Bring down that 3, make it x squared. Bring down that 2, multiply it to negative 3, giving me negative 6, x to the first, and you become 0. So that's first derivative. Second derivative is going to turn that 4 into a 12, 12x squared. Turn that into a 6. So we got 6x minus 6. Now set that equal to 0 and factor. I'm going to factor out a 6, which gives me 2x squared plus 1 minus 1. I should be able to factor that out. So, I mean, one of them's got to be positive and negative. One of them's got to be 1. One of them's got to be x, and one of them has to have a 2 in front of it. So if it's going to be negative, I'd imagine this is the 2, because you have 2x times negative 1. 2x squared, then 2x times negative 1, which is negative 2x. So I had it backwards. Let's move the 2 over here. Look at that. So x squared, 2x squared, minus x plus 2x minus 1. So that's what I need. All right, zero product property says that when you have factors multiplying to be equal to 0, you set each one equal to 0. Nothing happens here. If I have x plus 1 equals 0, then one of my inflection points is going to be -1 if I subtract 1 from both sides. If I take 2x minus 1, set that equal to 0, since I'm running out of space, add 1, divide by 2, my other inflection is going to be a half. Inflection point is going to be a half. So my inflection points, all two of them, are -1 and 1/2. I'm going to take that information and I'm going to make myself a sine chart. All right, I'm going to use the fact that I have -1 and a half, and I'm going to find the intervals. So what's going on between -infinity to -1? What's going on between -1 and a half? What's going on between a half and regular infinity? And I'm going to pick numbers in these three intervals, plug it into my second derivative, and see if I get a positive for concave up or a negative for concave down. So let's just pick the easiest numbers we can. I'll pick -10 for this guy. Let me move that down here. Will it make me do it now one by one? So let's do -10. Let's do 0. And let's do 1. So y double prime of -10 is going to be 12 times -10 squared plus 6 times -10 minus 6. Okay, let's do a little bit of mental math. -10 squared is 100. 100 times 12 is 1200. 1200 minus 60 is still really big. Minus 6 is still really big, so we get a positive number here. So this is positive, meaning from -infinity to -1, concave up. Okay, let's plug in 0 into our second derivative. 12 times 0 squared, I think I can handle that. Plus 6 times 0, I think I can handle that. Minus 6 is going to be 0 plus 0 minus 6, negative. So you're concave down. And let's see what happens when we plug in 1 to our second derivative. 12 times 1 squared plus 6 times 1 minus 6. 1 squared is 1. 12 times it is 12. 12 plus 6 minus 6 is still 12. Positive, positive. Now what this means is inflection points tell me where it's neither concave up nor concave down. That's the switch between concave up and concave down. Okay, that's what inflection points give me. This is the change. So what I know from this information is my graph is concave up on the intervals connecting -infinity and -1, but not including -1 because it's 0 there. It's neither. And from a half to positive infinity. It's concave down in the interval where my second derivative was negative, and that happened between -1 and a half. So, like I said, very, very, very similar to critical points and increasing and decreasing. You just had to take this one step further. So in the end, a lot of work. Really not that bad, though. I like it. Find the relative extrema of y equals x cubed minus 6x squared plus 9x plus 1. Well, what's relative extrema, you ask? I got you. That's a cubic. This is a cubic. This is going to look something like that, give or take. Who knows exactly what it's going to look like. But extrema stands for maximum or minimum, or both, depending on what you're dealing with, or multiple, The reality of having a cubic function that looks something like this is this guy's going to continue going up and to the right forever and ever and ever. This guy's going to continue going down and to the left forever and ever and ever. And if someone's like, what's the maximum? Well, it's going to be infinity and infinity. What's the minimum? Infinity and infinity in the negative territory. Relative extrema says, all right, well, let's pretend that that's not going on. Tell me where this thing peaks out and bottoms out, ignoring the fact that we have forever going on the left and the right. Where it peaks out is called the relative maximum. So I'll just say rel max. Where it bottoms out is the relative minimum. Now, the way we're going to use calculus to figure this out is we're going to find where our equation is increasing and decreasing. When we find out that our equation is increasing and then decreasing, we have ourselves a relative maximum. When we find out where our equation is decreasing and then increasing, we have ourselves a relative minimum. So in order to find increasing, decreasing intervals, we need to first go with critical points, which requires the derivative. So let's start out with that. The derivative of y prime, is going to be drop that 3 down, make the cube to squared, minus 6x, drop down the minus, 2 times 6 is 12, x squared becomes x, and then 9x becomes 9. Excuse me. All right, so critical points. Set that guy equal to 0. Okay, so I'll put CP, not for Chris Paul, but for critical points. If you're watching this video and you're learning calculus, you probably don't even know who Chris Paul is. I want to factor this guy out. Let's bring out a 3. X squared minus, let's see, divide a 3 from that gives me 4. Divide a 3 from that gives me 3. Let's keep factoring. 0 equals 3 times, let me think, 2 numbers that add up to negative 4 and multiply out to positive 3 are going to be negative 3 and negative 1 in no particular order. Now, if 0 equals a bunch of factors multiplied together, I can use the zero product property and set each factor equal to 0. So 3 equals 0 means nothing. X minus 3 equals 0 means that I will have plus 3, you get 3. If I have x minus 1 equals 0 plus 1, you get 1. So my critical points are going to be where x is 3 and where x is 1. This is where my line should change from increasing to decreasing, decreasing to increasing, so on and so forth. So I'm going to make myself a little sine table, sine graph, whatever you want to call it, SIGN. I care about 1, I care about 3. Okay, and this is going to be my y prime sine graph. Now what I'm going to do is this is going to tell me which intervals is increasing or decreasing. I'm going to pick numbers inside each interval. So negative infinity to 1, I can pick 0. 1 to 3, I can pick 2. 3 to infinity, I can pick, 10. And if I take these numbers, plug them into the derivative, and get a positive, it's increasing. If I get a negative, it's decreasing. So let's plug in 0. Y prime of 0 is going to equal 3 times 0 squared, which is 0, minus 12 times 0, which is 0, plus 9, which is a positive number. So this guy is increasing. Okay, this cubic is increasing from negative infinity to positive 1, then hits a horizontal tangent and maybe does something different. We'll see. Let's plug in 2. Y prime of 2 is going to be 3 times 2 squared, which is 12, minus 12 times 2, which is 24, plus 9, negative. So this is decreasing. If I plug in 10, and again, I don't know why. I chose 10 because it's large enough where I should obviously tell if it's positive or negative. 3 times 10 squared is 3 times 100, so 300, like that movie. forget what it's called, minus 12 times 10, which is 120, so minus 120, plus 9 is definitely going to be positive. So when x equals 1, I have, it goes up and then down. So at x equals 1, I have a relative maximum. At x equals 3, it goes down and then up, which means my graph is bottoming out. This is a relative minimum. Now, let's find the exact points. Okay, the way I find the exact points is I take those critical points that gave me a relative maximum or a minimum, and I plug them into the original equation. So I'm going to plug in 1 to the original equation. So y of 1 is going to equal 1 cubed, which is 1, minus 6 times 1 squared, which is minus 6, plus 9 times 1, which is 9, plus 1. So 1 minus negative 5. Negative 5 plus 9 is 4. 4 plus 1 is 5. So when I plugged in 1 to the original equation, I got 5. I'll deal with that in a minute. Well, no, I'll deal with it now. That tells me that my relative maximum, just one of them, is going to be the point 1, 5. Let's find out what my relative minimum is. All right, we'll plug in 3. So I have y of 3 is going to equal 3 times 3 times 3, 27, minus 6 times 9, so minus 54, plus 9 times 3, which is 27, plus 1. All right, so it's 27 plus 27 is 54, minus 54 is nothing, plus 1 is 1. So that equals 1. So my relative minimum is going to be 3, 1. Look at that. Didn't have to erase a thing. Aerosmith said, I don't want to change a thing. I said, I don't want to miss a thing. It's, I don't want to miss a thing. All right. This giant boot is my answer. Have fun with that. Find the absolute extrema on the interval -2, 4. Now I'm just going to make a random picture. Okay. In a previous video, we talked about relative maximum or minimum. And relative extrema is like, there's a relative max and there's a relative min, and there's a relative max and there's a relative mean. Well, absolute means, what if I take all of this and just like, we care about between here and here. So which one of these is the absolute maximum? Which one of these is the absolute minimum? You know, the absolute maximum could be right on the interval, or maybe it's not. Maybe the minimum is, I don't know. But now we're adding extra elements to it. So in order to do the absolute extrema, we still have to do the same thing that we would do for relative extrema, and that's find the critical points. First things first, I need the derivative. So y prime is going to equal 4, drop that down, x to the third minus 2x. Okay, drop the 4, make that a 3, drop the 2, make that a 1. So let me factor some stuff out. Set it equal to 0 and factor stuff out. I can bring out a 2x. When I do that, that becomes 2x squared. That becomes minus 1. When you have factors multiply together equaling 0, you're going to use the zero product property, set each factor equal to 0. So 2x equal to 0, divide by 2, x is equal to 0. 2x squared minus 1 equals 0. Add 1. Divide by 2. Take this square root and don't forget about your positive or negative. So my 3 critical points are x equals 0, positive square root of a half, and negative square root of a half. All right, so let's make ourselves a sine table with that one. We've got, let me see, this is y prime. We've got 0. We've got negative square root of a half. We've got positive square root of a half. So I guess the numbers that I can choose to go in between, I don't even know what square root of a half is. Let's consult the internet. What's the square root of a half? Okay, the internet says that this is negative 0.7 something. So while I plug in negative 0.5, why don't I plug in regular 0.5? Why don't I plug in negative 1? And why don't I plug in 1? Now, I'm going to plug it in to the derivative because by plugging it into the derivative gives me the opportunity of finding increase, decrease, all of that good stuff. Whenever it goes from increase to decrease, it's a maximum. Whenever it goes from decrease to increase, it's a minimum. Okay? So, I'm going to plug in negative 1 into the derivative. So that's going to be y prime of negative 1 is going to be 4 times negative 1 cubed, which is negative 4, minus 2 times negative 1. So negative 4 minus 2 times negative 1 is plus 2. So that gives me a negative, so you're decreasing. Okay, if I plug in negative 0.5, y prime of negative 0.5, I'm going to ask Siri to do this one for me because I don't have enough space to do it in my head. 4 times negative 0.5 cubed minus 2 times negative 0.5. All right, it's just positive. So you become positive. 4 times 0.5 cubed minus 2 times 0.5. That's negative. And let's plug in 1. I can do that without my old friend Siri helping me out. That's going to be 4 times 1, 1, which is 4, minus 2 times 1, which is 2, which is positive. So there you have it. All right. So I have a relative minimum. I have a relative maximum. I have a relative minimum again. So this picture is going to look something like this. Okay. It's going to look something like that. Here's the problem, though. What if, like, that is 4? Wouldn't that mean technically, since that part right there is higher than everything else, wouldn't that mean that the intervals 2 could be an option for an extrema? Yeah. So what I'm going to do is I'm going to take my 3 critical points and I'm going to take my 2 intervals and I'm going to plug them into the original equation to see what values I get. The largest value that I get is going to be my absolute maximum, and the smallest value that I get is going to be my absolute minimum. So let's start out with the endpoints. Let's just do it. Okay, y of negative 2 is going to be the same as negative 2 to the positive 4th power, which is 2 times 2 is 16, minus negative 2 times negative 2, which is 4. That gives me 4. No, it gives me 12. It gives me 12. Trying to do too much. All right, so one endpoint, check. The other endpoint, about to check. 4 to the 4th is going to be, I believe that's 256. 4 to the fourth power. 256. 256 minus 4 squared, a fun game, becomes 240. Definitely going to need Siri for these ones. Y of negative square root of a half. Oh, I already know what that one's going to be. Jumping the gun. Or do I? No, I don't. If I do 1 times 1 times 1 times 1, right, I get the square root of 1 on top, which is 1. If I do 2 times 2 times 2 times 2, that's 16. So the square root of 16, I get a fourth on the bottom, minus the square root, negative square root of a half is just a half. So you become negative 3/4? Yeah. No, negative 1/4. A little paranoid about that. What is the square? What is the square root? Oh my goodness gracious! What is the square root of 1/2 to the fourth power? Yeah, all right. I did it right. I did it okay. What's 1/4 minus a half? Negative 0.5. All right. Let's plug in 0. Finally, an easy one. You're going to get 0. And if I plug in positive 1/2 in a square root, it's going to give the same thing as that. So this is fun. I have an absolute maximum for sure, and it's u. So my absolute maximum is the point 4, 240, and I have 2 absolute minimums. And my absolute minimum is going to be the points negative square root of a half, negative 1/4, and positive square root of half, negative 1/4. Whew, gross. Didn't like it. But it's done, and it's done, and it's done correct and well. A supermarket employee wants to construct an open-top box from a 14 by 30-inch piece of cardboard. So that was me trying to draw a rectangle. Let's try it one more time. There we are. Not bad. So we'll call you 30. We'll call you 14. That is sentence number 1. Sentence number 2. To do this, the employee plans to cut out squares of equal sides from the 4 corners of the 4 sides and bend it upwards. All right, so we're starting to get a picture here. Here's a square. We'll call you X. Here's a square. We'll call you X. Here's a square. We'll call you X. Here's a square, we'll call you X. So each sides here of the square are called X's. Lots of X's, kind of like me and my dating history. Hey-o. It's not true. What size should the squares be in order to create a box with the largest possible volume? So let's try to visualize what's going on here. All right, after we cut out these X's, and let me try to draw a picture that looks like that. Not bad. Can I make it smaller? Yeah. All right. That's the best I can do. Let's move that over. Let's do that. Oh, not bad. Let's do that. Let's do that. Not bad again. And let's do that. And let's do that. I'll take it. So what's going to happen is we're going to take that and we're going to bend these upward. Bend them up, bend them up, bend them up. When you bend them up, you have yourselves a cardboard box without a top to it. Okay, cardboard box without a top to it. That's me attempting to draw a cardboard box. It looks awful. But there you have it. Now, I have to figure out what these measure up to. Well, if I were to fold that up and pretend that this is that, this side length is not 14. It's 14 minus x because I cut out 2 of the sides there. Again, when I bend that up, this is that. This little length is that. And so that length is 14 minus x, so 14 minus 2x. Similarly, this whole thing was 30. But after I bend these up to create that length, it's 30 minus 2x. And then I have the height. Since I bend it up, it's going to be the size of the squares that I cut out, x. My job is to maximize the volume. So we need to write ourselves a volume formula. So volume is normally length times width times height. In this case, our volume is going to be that times that times that. So we have x times 30 minus 2x times 14 minus 2x. So it doesn't really matter. We're going to have to multiply things anyway. So let me distribute that x. I have x squared in parentheses, just kidding, 30x minus 2x squared. I don't know why I jumped out to x squared. But we have 30x, x times negative 2x is negative 2x squared. And then we're going to FOIL that out to 14 minus 2x. All right, so 30 times 14, that's 420. So we've got ourselves 420x. 30x times negative 2x is minus 60x squared. Negative 2x squared times 14 is going to be minus 28x squared. And then 2x squared, negative 2x squared, and negative 2, positive 4x to the third. Let's combine like terms, put this all in standard form. We've got ourselves 4x cubed, negative 88x squared, and positive 420x. Now, I found my volume formula, and there it is. If I'm going to maximize it, I need to take the derivative and find critical points. This is very, very, very similar to when you do extrema, maxes and mins. But I'm going to add a little extra thing to it. It's not just relative extrema. I have to go one step further. Before I even do any of that, I got to get critical points. So V prime is going to equal 12x squared. Let's multiply that minus 176x plus 420. Get rid of the x and stop making so many typos and writing errors. Now, in order to do critical points, I have to set it equal to 0, and I'm going to factor the 12 out because I think I can. Oh, I can't factor out a 12. Well, this is frustrating. Let me see. I can factor out a... Can I factor out a 6? No, I can't, but I can factor out a 4. If I do that, that leaves me with 3x squared minus, what is that, 44x plus 105. All right, I could use whatchamacallit if I wanted to. Quadratic formula, but give me one second. Oh, you know what? That's 35 and 3. 35 and 3. Ooh, 3x minus 35 and x minus 3. All right. I'm going somewhere. So my critical points so far are going to be, if I set these each equal to 0, okay, first off, 4 means nothing. If I set that equal to 0, one of my critical points is 3. If I add 35 and divide by 3, that gets me 10 and 2/3, I believe. No, 11 and 2/3. But since this is a maximization problem, I'm bound by real life endpoints. So this is more like the absolute maximum and minimum where I have an interval to deal with. If I'm cutting x's out, I can't cut any more than 7. So I have legitimate endpoints of 0 because I can't, have 0 squares to cut out. And I can't go further than 7. If I were to try to cut out x's, if I were to try to make 8 my x, that's too much to cut out. So 7 is one of my endpoints and 0 is one of my endpoints. But since I found out that 7 is an endpoint, you can't work. So what I'm going to do is I'm going to find the volume using this formula right here by plugging in 0, which I know will not work, 7, which I know will not work, and 3, which is going to have to work. So let's do it anyway. Volume of 0 is going to be blah, 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 0 cubed minus blah, blah, blah times 0 times plus blah, 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 0. So I get 0. So that makes sense. If I can't fold it up, I get 0. Now let's try 7. If I plug in 7, the original volume problem gave me that. So 14 minus 2x. So what's going to happen is this part is going to become 14 minus 14. So let's just make believe that you understand what I'm doing. If I were to plug in 7, I'm going to get 0 again. So 3's got to be my only guy. So let's plug in 3. 4 times 3 cubed minus 88 times 3 squared plus 420 times 3. It's going to give me some number. And what it's asking me here is you don't have to find that number. Just find out the sizes of the squares in order to make it work. Well, 3 is going to be my guy. So 3 inches is going to be my answer. So maximization problems, optimization problems are pretty brutal, this being one of them. But, after all of that work, I think we finally figured that out. It's not going to be the prettiest answer, but it'll do. Okay, let's sketch a graph using rules for increase, decrease, and concavity. So we're not looking for perfection, we're looking for somewhat accuracy. Let's do the first thing by doing increase. In order to find increase and decrease, you're going to take the derivative, which gives you critical points. So let me write that over here. It's going to be fun trying to fit this all in one screen. Probably not going to happen, but that's all right. Critical points are going to be found by taking the derivative. So you're going to bring that 4 down, and the 4 over here cancels each other out. So that leaves you with negative x cubed plus 2x, and then nothing. Set it equal to 0. Let's factor out a negative x. Yeah, let's factor out a negative x. When we factor out a negative x, that leaves us with x squared minus 2. Set these both equal to 0. So 0 is going to equal x. And negative x, which means x equals 0. Sorry if I jumped ahead too fast. X squared minus 2 equals 0. Add 2 gives you this. Square root both sides. Don't forget to attach a plus or a negative over here. And so my critical points are going to be negative square root of 2, 0, and the square root of 2. So remember when I said about a minute ago, it's going to be hard putting all this on one screen? It ain't happening. But what I have right now is I have a critical points concavity, or not, I'm sorry, not concavity, critical points increase, decreasing starting point. So I'm going to make myself a sine chart, S-I-G-N, not S-I-N. We're going to put negative square root of 2 on there. We're going to put 0 on there. We're going to put positive square root of 2 on there. In order to find increase and decrease and where that happens, all right, I'm going to pick numbers that aren't exactly these guys but live on the interval. So I can pick like, I don't know, negative 5, negative 1, 1, and 5. I'm going to plug these into the derivative, which is this guy right here, do a little bit of math. If I get positive, that means it's increasing on that interval. If I get negative, that means it's decreasing on that interval. So let's take our y prime and plug it in. Y prime of -5. Let's try to do this mentally. All right, -5, there's my derivative. -5 is going to be -5 cubed is going to be -125. That negative cancels it out. So 125 minus 10 is going to be positive. So this is increasing here. If I take y prime of -1 and plug in -1, I get -1 to the third power, which is -1, times the -1, which is +1. But I'm going to add +1 to 2 times -1, which is -1. So this is negative. Again, if you're like, what happened? Just throw it in a calculator, buddy. Trust me on this one. Y prime of 1. Okay. -1 cubed is -1 plus +2 is going to be positive. So I'll move that over there. Positive. And then if I plug in regular 5 into the derivative to see if it's positive or negative, I will get 5 cubed, which is 125. That negative out there is -125. -125 plus 10 is still pretty negative, which means that's pretty decreasing. So this is what I know so far. This guy is increasing all the way up until -√2, whatever √2 is, like 1 point something, 1.7, I believe. Maybe not, maybe 1.4. I'll ask Siri to help me out with that one. And then it starts decreasing. It hits an x of 0, so it hits the y-axis, starts increasing again, and at √2, it starts decreasing again. So this is happening like that. But that's not good enough. Need more specifics than that. Need a lot more specifics than that. So what I'm going to do is I'm going to start my inflection points up here. I'll probably end up erasing that when all is said and done, but we'll see. We'll see what I can fit on this one little screen. So to find the inflection points, I care about the second derivative. So the first derivative was -x cubed plus 2x. So the second derivative has me bringing that 3 down and squaring it, -3x squared, and then getting rid of that x to make it +2, and I really hate this problem. Inflection points, set it equal to 0. Let's factor out a -3. No, let's not factor out a -3. Let's just leave it like that. Factoring out a -3 gets me nowhere. I could subtract 2. -2 is equal to -3 over x squared. Divide everything by -3. Divide everything by -3. I get 2/3 equals x squared. Square root both sides, positive or negative, and my inflection points exist at the square root of, I forgot to write out square root. My inflection points exist at negative square root of 2/3 and positive square root of 2/3, like that. So I'm going to make another sine table. But this time, this is going to be for concavity. So let me put my concavity info right here. All right, I have negative square root of 2/3 and positive square root of 2/3. Now, the square root of 2/3 is, I know, somewhere in between 0 and 1. So again, I need to choose numbers that live in between these intervals, but not exactly on those intervals. So I'll choose 0, I'll choose -1, and I'll choose +1. So when I find the y double prime of that number, it'll tell me if it's positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. So y prime of -1, if I plug in -1 to y double prime, I'm going to get -3 times -1 squared. So -3 times 1, -3 plus 2 is negative. So right here we have concave down. If I plug in 0 for y double prime, I get 0 plus 2, which is positive, concave up. And if I plug in regular 1 to y double prime, so y double prime of regular 1, I get literally the exact same as I get over here. So I get negative, which makes that concave down. All right, time to sketch. Now, again, the purpose of sketching is you're not looking for perfection. You're looking for like an accurate representation of what this picture looks like. So what's the lightest color that I can use on this thing? Like a nice yellow. Let's get a nice yellow up in here, like a gold. All right. So there's my coordinate plane that is awfully drawn. You can barely see it. The critical points and the inflection points are what really matter. Okay, so I care about the square root of -2. I care about the square root of 2 over 3, the negative square root of 2 over 3. I care about 0. I care about the positive square root of 2 over 3. And I care about positive square root of 2. And I think I've hit everything. Negative root 2, negative, I got it. Zero's there. I got it. Now let's do some drawing. I increase, I'm increasing until I hit negative square root of -2. So let's draw something that's increasing. Once I hit -2, I begin decreasing until I hit 2/3. Once I hit 2/3, I start going concave up. So right now, you can see that -2/3 to the left is concave down. But once I hit -2/3, I start concave upping until I hit 0. Once I hit 0, my decrease becomes an increase and continues that trend until I hit negative square root of 2/3, where I become concave down again. Once I hit the square root of 2, my increase becomes a decrease, and so I get some kind of weird thing that looks like that. All right? Again, this is a sketch. This is not perfection. If I wanted perfection, then I would take all of these numbers, plug them into the original function, and get specific points. I could have done that, but I didn't. You know why? Because I have one screen here and I don't have all the time in the world. And I'm sure I have a video somewhere on the internet that involves me doing this. So, go find it and like and subscribe while you're at it. All right? That's that. Bye. A particle moves along a horizontal line where its position is given by the function below. S of t equals t cubed minus t squared minus 5t. Find the velocity and acceleration at t equals 3 seconds. Well, let's do this. Let's do the velocity on the left. Let's do the acceleration on the right. All right, let's do the velocity function in red, or if you're colorblind, gray. Velocity is found by taking the derivative of your position function. Okay, so this. So I need to take the derivative of s. So s prime is going to be drop down that 3t squared minus 2t minus 56. Okay, power rule, power rule, power rule. This is the velocity function right there. Let me rewrite it out. The velocity function is 3t squared minus 2t minus 56. What I care about is what happens at 3 seconds. So v of 3, which is s prime of 3, is going to be 3 times 3 squared minus 2 times 3 minus 56. Okay, 3 times 3 times 3 is 27, minus 6 minus 56. The negatives combine to make negative 62. Negative 62 plus 27 is negative 35. So that's the velocity at 3. Okay. What this means is I have seconds here, units. It doesn't say feet. It doesn't say any, measurement. What this means is this is going backwards, okay, or downwards. If it's a negative velocity, that means you're like, if I were to drive 35 miles an hour, I'm driving forward. If I were to drive negative 35 miles an hour, I'm driving backwards 35 miles an hour, and this represents going backwards. Now, if the velocity, which is speed, right, but velocity is allowed to be negative, speed's not. So just another thing to put in another feather to put in your hat. If I wanted to find acceleration is the second derivative of the initial function, of the position function. So S double prime of t. So this is going to be my acceleration function. So S single prime, its derivative, drop that 2 down, becomes 6t minus 2, get rid of the t. This is the acceleration function. Let me get rid of the prime. Oh my gosh, I really didn't need that prime there, and so I just got rid of everything. All right. The acceleration function is given to us by 6t minus 2. Now, acceleration is what's going on at the moment. So what's happening at 3? Are you accelerating? Are you decelerating? Are you speeding up? Are you slowing down? Let's find out. A of 3 is going to be 6 times 3 minus 2, which is 18 minus 2. So A of 3 is 16. So let's attach units of measure to this, right? Velocity is like miles per hour, feet per second. I have 3. It doesn't give me a unit for its position, so we'll say units per second. For acceleration, it's units per second squared. Now, what's happening at this 3-second mark is I'm hitting the pedal to the metal. I'm accelerating. I'm going faster, but I'm going backwards while doing it. So in a second, I'll be going negative 38 miles an hour or something like that. But acceleration is positive, which means I'm speeding up while going backwards. That is how we do this problem, and that is the velocity and acceleration example dunzo. All right, let's calculate the limit of this guy right here. We have the limit as x approaches 0 of e to the x minus e to the x, negative x, all over x. So I guess if I plug in 0, I get 1. If I plug in 0 again, minus 1, I get 0 on the top. But if I plug in, 0 over 0, that's not possible. That's indeterminate. Well, there is a section from early on in calculus that says this is no good. You can't have 0 over 0. Can't have it. So what happens when you do that? Normally you try to find ways to make this just one, like this one function or this one fraction, not one fraction, but I can't do that here. So there's a rule called L'Hopital's rule that says that this guy is equal to the derivative of the top over the derivative over the bottom and take the same limit. So what I'm going to do is I'm going to take this guy, I'm going to rewrite the limit as x approaches 0 of e to the x. So I'm going to take the derivative of e to the x. So e to the x is e to the x minus, I'm going to take the derivative of e to the negative x. So this is chain rule. The chain rule says you take the derivative of the outside, which is e, so e, keep the inside, but multiply everything times the derivative of the inside. So the inside is negative x. The derivative of negative x is negative 1, so just make that negative. So e to the negative x became negative e to the x, so this becomes e to the negative x, positive. Take the derivative of the bottom 2. That becomes 1. Now I plug it in and see what happens again. So I get e to the 0 plus e to the negative 0 over 1. E to the 0 is 1. E to the negative 0 is the same thing as e to the 0, which is 1 over 1, and I get 2. So again, the trick here is if you plug in your limit and you get 0 over 0, which is impossible, take the derivative of the top, take the derivative of the bottom, try it again. If it happens again, do the exact same thing. Repeat until you finally get yourselves a solid number, which is what I got. The answer here is 2. Let's calculate the limit of x going to x or pi over 2 of 3 secant x minus 3 tan x. So let's just plug this stuff in. X goes to pi over 2, 3 secant, wait a minute. Secant pi over 2 is undefined. I can't do this. This is going to be an undefined answer. So what do I do if it's an undefined answer? Do L'Hopital's rule. L'Hopital's rule says that let's do this. Let's make life a little easier. Let's rewrite these guys out. L'Hopital rule says that if we get something that's undefined, we could take the derivative of the fraction, the derivative of the top over the derivative of the bottom. No, I don't see a fraction there. But you know what I do see? Let's write this out and let's get rid of all this limit stuff. I'll attach it later. Okay, 3 secant x. Secant is 1 over cosine. So this is the same thing as 3 times 1 over cosine x. Tangent is the same as sine over cosine. So sine x over cosine x. Now let's write this out a little more convenient. Let's put the 3 up top. Let's put the cosine on the bottom. Now, why did I make that one big denominator? Because these two will combine. So on the top, minus 3 sine x, so minus 3 sine x. And now what I can do is take the derivative of this guy, of the top, and the derivative of the bottom, and see what magical things happen. Now, by the way, if you're wondering, well, why can't I just plug in pi over 2 into x? Because cos of pi over 2 is 0, so you're still going to get undefined. So x is pi over 2. Let's take the derivative of the numerator. The derivative of 3 becomes nothing. Now I have negative 3 sine x. The derivative of sine is regular cosine, so I'm left with that. In the denominator, let's take the derivative of cosine, which is negative sine x. So now what I have is, and I'm writing this out knowing that there's a possibility that I might have to keep going, but we'll see. We'll see. Negative over negative is a positive. I now have 3, and cosine over sine is cotangent. So I have cotangent x. Now what I'm going to do is I'm going to calculate 3 times the cotangent of pi over 2. Now the cotangent of pi over 2 is 0. And 3 times 0 is 0. So at the end of the day, this whole thing has a limit of 0. Now we know that with limits, you're not looking at exact answers, because if I were to try to once again plug in pi over 2, it's not going to work. It's going to be undefined. But where is my graph going as I approach pi over 2? To 0. It works out. You get a hole there, but that's all right. That's my answer. L'Hopital's rule.